The Baltic Sea at 2:51 a.m. in October carries the specific tension of a sea that knows it is not open ocean. The Gotland Basin, where USS Ramage is operating, is 54 meters average depth, deep enough for submarines, shallow enough to feel enclosed, and bounded to the north and south by transit corridors that carry the ferry traffic, tanker runs, and container routes of a body of water that 8 nations depend on. At night, in overcast conditions, the AIS picture on the ECDIS shows the surrounding shipping as moving lights on a dark chart. A midnight ferry from Stockholm to Turku on a bearing of 047 at 21 knots. A Panamax tanker making 14 knots southbound on the western traffic lane. Half a dozen smaller contacts distributed across the basin. The Ramage knows where all of them are. They do not know that the Ramage is here, because the Ramage is running darkened ship on a freedom of navigation transit that the Baltic Fleet's surface surveillance has been tracking for 3 hours. USS Ramage makes 21 knots on a southwesterly heading, threading the Gotland Basin corridor toward the Fehmarn Belt and the exit to the North Sea. She has been at general quarters for 22 minutes. At 2:29 a.m., the electronic warfare operator classified a P-800 Oniks battery on the Russian Baltic enclave coast in a targeting mode. A distinctive emission profile that the operator has seen in simulation exercises and in the EW library, but has not previously encountered in live conditions in this theater. He reported it in 4 seconds. The commanding officer had the ship at GQ within 15 seconds of the report. At 2:44 a.m., the Aegis engaged the inbound Oniks with 2 SM-6 missiles staged at 11-second intervals. The Oniks is a capable system. Mach 2.5 in cruise phase, Mach 2.7 in terminal sprint, 300-kilogram warhead. A missile designed for exactly this kind of engagement against a surface combatant in a constrained sea. The first SM-6 intercept achieved proximity detonation at 31 miles. The Oniks's airframe disrupted, its guidance disabled, its terminal sprint aborted. The second SM-6 engaged the fragmenting airframe at 18 miles and dispersed the debris field across the northern transit corridor. 2 missiles, 1 Oniks. 11 seconds of engagement from the moment the first missile left the VLS cell to the confirmation of the second detonation. Most of the debris passed over and clear of the Ramage. One piece did not. The fragment, a section of the Oniks's external airframe cladding, approximately 3.4 kilograms, trailing burning propellant residue, struck the Ramage's aft mast at 2:31:08 a.m. The aft mast carries communication antennas, the aft navigation radar, and the primary cable conduit runs that connect the ship's after steering room electronics to the bridge steering control system. The burning fragment impact on the mast is superficially minor. The mast structure is intact. The navigation radar antenna is undamaged. The communication antennas are undamaged. The cable conduit at the aft mast base, however, has been punctured by a secondary fragment that separated from the primary piece on impact. The puncture is 8 millimeters in diameter. It admits the burning propellant residue into the conduit interior. The conduit interior at the aft mast base contains 47 cables. Of these 47 cables, 12 are the rudder control signal cables. The cables that carry the steering command signals from the bridge helm control to the aft steering room's electro-hydraulic steering control unit. These cables carry 24-volt DC control signals, not high-power conductors. They are signaling cables, and their insulation is rated for significant thermal tolerance. The conduit is a controlled environment for a reason. But the burning propellant residue that enters through the 8-millimeter puncture is not a thermal challenge within rated parameters. It is a direct ignition source. The propellant residue burns at approximately 1,200 degrees Celsius at its ignition point and sustains combustion in the conduit interior for approximately 19 seconds before exhausting itself. In 19 seconds of 1,200-degree combustion in a sealed conduit containing 47 cables, the insulation on every cable in the conduit is partially or fully compromised within a 30-centimeter zone centered on the puncture point. 12 of those cables are rudder control signal cables. Of those 12, 7 have conductor exposure from insulation burned through. Of those 7, 4 have been physically severed. The conductor itself, not just the insulation, has burned through at the highest temperature point. The remaining 3 have partial conductor exposure but maintain physical continuity. At 2:31:28 a.m., 20 seconds after the fragment impact, the bridge helm control reports no rudder response. The helmsman reports 0 response from the steering servo. The officer of the deck orders emergency rudder control to the aft steering room. The aft steering room operator reports aft steering control also showing no response. The steering control unit is receiving no signal from the bridge, and the manual backup mode, which allows the aft steering room operator to drive the rudder directly, is showing a partial signal error that is preventing the backup mode from engaging cleanly. The partial signal error in the backup mode is caused by the 3 cables with partial conductor exposure that have maintained physical continuity but are now generating noise. Erratic voltage signals from the exposed conductors contacting each other and the conduit wall through the burned insulation. The backup mode signal verification circuit is interpreting this noise as a fault condition and refusing to engage. The aft steering room has manual hydraulic capability. It can physically move the rudder by operating the hydraulic control valve by hand, bypassing all electronic control. But the hydraulic manual override requires a specific procedure to activate and takes approximately 4 minutes to complete. The Ramage is at 21 knots on a bearing that, maintained for 11 minutes, will bring her into the path of the southbound Panamax tanker that is 7.4 nautical miles ahead on a reciprocal course. The tanker's AIS transponder shows it at 14 knots southbound, 65,000 tons, displacement requiring 3.8 nautical miles to stop from 14 knots. The Ramage has 11 minutes to restore steering or take an alternative action. If the Ramage maintains 21 knots on the current course, the closest point of approach to the tanker, uncorrected, is approximately 0.2 nautical miles. Within the Maritime Collision Regulations' dangerous proximity threshold for vessels of this size in a constrained corridor, the commanding officer is informed of the steering casualty at 2:31:35 a.m., 7 seconds after the helm reported no response. He immediately orders propulsion reduction to 5 knots on the port shaft and 10 knots on the starboard shaft, asymmetric thrust to induce a starboard turn that will move the Ramage's course away from the tanker's track while the steering casualty is being addressed. The asymmetric thrust approach is a speed-dependent maneuver. At 21 knots, it produces a slow, gentle turn. As speed reduces, the turning rate increases because the asymmetric thrust becomes a larger proportion of the total thrust acting on the ship. As the ship slows from 21 knots toward 10 knots, the turn rate increases. This buys time. It does not fix the problem. The commanding officer also orders the officer of the deck to contact the tanker on VHF Channel 16, inform it of the navigational situation, and request the tanker take avoiding action to starboard. This is the correct action under the International Collision Regulations. A vessel with steering difficulties is required to signal its situation and coordinate with approaching vessels. The tanker acknowledges on Channel 16 at 2:31:58 a.m. and reports it is altering course to port, away from the Ramage's track. The closest point of approach, now with both vessels taking avoiding action, opens to approximately 1.4 nautical miles. The immediate collision risk is managed, but the Ramage is still without steering control in the Gotland Basin, at 5 to 10 knots and slowing. With the Fehmarn Belt 180 nautical miles ahead and a ferry corridor to the north, she cannot complete the transit without rudder control. In the aft electronics maintenance space, the small compartment adjacent to the aft steering room where the rudder control electronics are mounted. The electronics technician has been assessing the cable casualty since the failure was reported. He reached the aft mast cable conduit entry point at 2:32:15 a.m. and has been using a cable tracer and continuity tester to map the damage. The cable tracer works by injecting a known signal at one end of each cable and reading the signal at the other end. An intact cable passes the signal cleanly. A severed cable passes nothing. And a partially damaged cable with conductor exposure passes a distorted signal that the tester characterizes as noise. He works through all 12 rudder control cables systematically, one at a time, recording each result in his maintenance log. The process takes 1 minute and 25 seconds. He has done it before. During a port visit cable inspection 3 months ago, on a different cable bundle, under comfortable conditions. He does it now at 2:32 a.m. in a compartment lit by emergency red, with the ship at 8 knots and the Baltic Sea making its small, persistent case against the hull outside. His assessment at 2:33:40 a.m. relayed to the commanding officer. 4 cables physically severed. Tester reads no signal. Confirmed open circuit on all 4. Conductor has burned through. 3 cables with conductor exposure causing signal noise. Tester reads distorted, erratic signal, consistent with conductors in contact with adjacent materials. 5 cables intact. Tester reads clean signal on all 5. Insulation may be thermally stressed, but conductors are unbroken and isolated. Of the 12 total rudder control signal cables, he assesses 7 as requiring some form of repair and 5 as potentially serviceable. Of the 5 intact cables, 3 carry the primary forward command signals to the steering control unit, and 2 carry the feedback signals from the steering control unit back to the bridge. With 3 primary and 2 feedback cables intact and usable, the system might be able to operate with reduced signal integrity. But the 3 noise-generating cables are contaminating the signal environment in the conduit. And the steering control unit's signal verification circuit is rejecting all inputs because of the noise. The solution, as the electronics technician explains it to the chief engineer at 2:34:02 a.m., is not to repair the severed cables. Cable splicing takes at minimum 40 minutes in the best conditions in an accessible space with proper tools. The solution is to isolate the noise-generating cables so that the 5 intact cables can function without interference. If the 3 cables with conductor exposure can be physically isolated, their conductors separated from contact with each other and the conduit wall, the signal noise they are generating will stop, and the steering control unit's verification circuit may accept the clean signals from the 5 intact cables. Physically isolating the conductors of a cable in a conduit requires access to the cable at the damage point. The damage point is inside the conduit, at the puncture location 2 meters above the conduit entry panel. The conduit is 60 millimeters in diameter. The conduit entry panel, when opened, provides access to the interior. But 60 millimeters is narrow for the tools needed, and the access is a 30-meter run from the nearest service entry. The option of working from inside the conduit is not an option. The option of working from the aft mast cable entry point requires climbing the mast at 2:34 a.m. in the Baltic Sea. Manageable in daylight with a safety harness. Possible at night with a battle lantern and a safety line. The electronics technician says the mast work is the right approach. He says he can reach the damage zone from the aft mast cable entry panel at the mast base. Run a temporary bypass cable from the intact cables at the conduit entry to a direct connection at the aft steering control unit, bypassing the damaged conduit section entirely. The bypass cable would need to be run externally, along the mast structure and down the ship's superstructure exterior, rather than through the damaged conduit. He says he needs 30 minutes, a cable run of approximately 14 meters, a weather-rated junction connector from the electrical repair kit, and a second person to hold the battle lantern and manage the safety line. 30 minutes. The Ramage is at 8 knots and still turning slowly starboard. The tanker has altered course and is now at 2.1 nautical miles and opening. The ferry from Stockholm to Turku is 9.4 nautical miles and not a factor. The asymmetric thrust is maintaining a manageable situation, but the ship is not under directional control. It is yawing slowly in response to the asymmetric propulsion and the wind, which is running 12 knots from the northwest and pushing the ship slightly onto an unwanted heading. In 30 minutes, the ship's position in the Gotland Basin will be approximately 4 nautical miles southwest of its current position, on a course that will have drifted approximately 8 degrees left of the intended heading. Not a crisis, not a course correction that asymmetric propulsion can maintain precisely. The bypass cable is a workable solution. The chief engineer authorizes it, then immediately asks the one follow-up question that the situation requires. What is the fastest alternative if the bypass does not achieve clean signal at the steering control unit? The electronics technician says the next option is physical isolation of the noise-generating cables at the conduit entry panel, separating the damaged conductors from the intact ones in the accessible zone at the mast base, rather than running the bypass externally. He says it is faster, but he does not know if he can reach the damage zone from the entry panel, because the puncture is 2 meters into the conduit interior, and the entry panel opening is 60 millimeters. Barely enough to work with tools. He says it is worth attempting first, before the 30-minute bypass procedure. Because if it works in under 5 minutes. The chief engineer says, attempt the isolation first. If it does not work in 6 minutes, begin the bypass. The electronics technician and the boatswain's mate reach the aft mast at 2:35:15 a.m. The aft mast is in the stern section of the ship, accessible from the fantail. At night, in October, in the Baltic, at 8 knots ship speed. The apparent wind on the fantail is approximately 20 knots from the forward arc. The mast is approximately 9 meters above the deck. The cable entry panel is at the mast base, 1.5 meters above the deck, not requiring a climb, but requiring kneeling in the apparent wind with a battle lantern and tools while the ship moves through the sea. The boatswain's mate holds the battle lantern and the safety line. The electronics technician opens the mast base cable entry panel. The cable entry panel reveals the conduit interior at the damage zone. The puncture is visible from inside the panel as an 8-millimeter hole with char marks around its edges, with the damaged cables running through the conduit visible as a bundle of 47 conductors, some visibly blackened over a 30-centimeter section centered on the puncture. The 3 noise-generating cables are identifiable by their insulation condition. The burn-through has exposed the copper conductors at the damage point, and the conductors are touching the adjacent cables and the conduit wall. The electronics technician reaches into the panel with a cable separator tool, a small nylon wedge designed to push cables apart in a conduit, and physically separates the 3 damaged conductors from the adjacent intact cables. He inserts nylon insulating sleeves over the exposed conductor sections, securing them with cable ties to prevent the conductors from making contact with anything in the conduit environment. The 3 noise-generating cables are now isolated. Their conductors are sheathed in nylon. The 5 intact cables remain connected to the bridge and the aft steering control unit. The signal noise in the conduit disappears. At 2:39:47 a.m., the aft steering control unit's signal verification circuit receives clean signals from the 5 intact rudder control cables. The verification circuit accepts the input. The bridge helm control shows steering responsive. The officer of the deck tests the rudder. 5 degrees port. The rudder moves. 5 degrees starboard. The rudder moves. The commanding officer orders propulsion normalized. Both shafts to 15 knots, equal thrust. and course to resume the transit heading. The Ramage comes onto her transit course at 2:41:12 a.m., elapsed time from steering casualty to restoration, 9 minutes and 44 seconds. The bypass cable run that the electronics technician had prepared for is not needed. The conduit isolation achieved with the cable separator tool and nylon sleeves was sufficient. The existing intact cables are carrying the signal without external bypass. The work that was expected to take 30 minutes was completed in 4 minutes and 47 seconds because the problem, when examined at the cable entry panel, was not the 4 severed cables, but the 3 cables generating noise. Remove the noise, and the intact cables can do their job. The 4 severed cables, the permanent repair, will require yard attention. The conduit will need to be opened, the severed sections replaced, and the insulation restored throughout the damage zone. Until that work is done, the rudder control system is operating on 5 of 12 design cables with reduced signal redundancy. The steering is functional. The redundancy is reduced. The chief engineer posts the aft mast cable entry panel on a 30-minute watch rotation for the remainder of the transit, with a spare nylon sleeve kit and cable separator tool staged at the mast base, in case any of the isolated conductors work free and re-establish contact. None of them do. The nylon sleeves hold for the 31-hour transit to Kiel. The aft mast cable conduit repair is completed at the Kiel Naval Facility over 6 days. The VHF Channel 16 recording of the Ramage's communication with the Panamax tanker during the steering casualty period was reviewed by the Fleet Navigation Officer during the post-event debrief. The communication was assessed as procedurally correct, professionally executed, and effective in preventing a dangerous proximity situation. The tanker's master, in a subsequent message to the Fleet Operations Center, described the Ramage's crew as professional in a difficult situation. The Fleet Navigation Officer noted this in the debrief report and did not elaborate on it. The description was accurate. It required no elaboration. One P-800 Oniks airframe fragment, 3.4 kilograms, punctured the aft mast cable conduit at 2:31:08 a.m. Burning propellant residue entered the conduit and burned for 19 seconds at approximately 1,200 degrees Celsius. 4 rudder control signal cables severed, 3 cables with conductor exposure generating signal noise, 5 cables intact. Rudder steering responsive to helm lost at 2:31:28 a.m. Asymmetric thrust maneuvering established to maintain safe course while repair was conducted. VHF Channel 16, coordination with approaching tanker. Closest point of approach open to 1.4 nautical miles. 3 noise-generating cables physically isolated using cable separator tool and nylon insulating sleeves at aft mast base panel in 4 minutes and 47 seconds. Steering restored at 2:39:47 a.m. Total casualty duration, 9 minutes and 44 seconds. Permanent repair scheduled for Kiel. Ship status operational. The 9 minutes and 44 seconds between the loss of steering and its restoration were managed without panic and without improvisation in the negative sense of the word. Improvisation in the sense that the solution was assembled from components that were understood and available, applied to a problem that had not been specifically anticipated, but whose underlying structure was familiar to everyone who dealt with it. The commanding officer used asymmetric thrust because he knew his propulsion system. The electronics technician isolated the noise-generating cables because he knew his cable system. The boatswain's mate held the light steady, and the safety line taut because he knew his job. None of them were doing something new. They were doing something familiar in an unfamiliar combination. The cable separator tool that the electronics technician used, a nylon wedge, standard issue in the shipboard electrical repair kit, has a catalog number and a manufacturer's specification and a replacement cost of approximately $11. It was the most operationally significant piece of equipment on USS Ramage for the 4 minutes and 47 seconds it was being used. The tool does not know this. The person using it does.